Yes, welcome back to the next session of Design of Prestressed Concrete Elements course. So in the last session, we have completed module number 1. So in that, we have been worked out or learned various concepts to analyze the PSC beam with using the various concepts. And also we have came to know or discussed the concept of pre-stressing or how to induce the pre-stressing inside the pre-stressed concrete beam and so on. So with these introduction and analysis idea, so let us move to the further, that is coming to the next module. The module number 2 discuss, we are going to discuss laws of pre-stress in pre-stressed concrete beam. Next, the deflection, that is the deflection of pre-stressed concrete beam, and the crack width. So these two concepts we are going to discuss in this particular module number 2. So let us get into the module number 2. So first, let me define what is loss of pre-stress. Okay, what is loss of pre-stress? Okay, so the initial pre-stress in concrete undergo a gradual reduction with time from the stage of transfer due to the various causes is termed as loss of pre-stress. I will repeat. The initial pre-stress in the concrete undergoes a gradual reduction or gradual loss with time from the stage of transfer due to the various causes. Here the keywords are initial pre-stress, okay, stage of transfer, and due to various causes, it will undergo reduction. So now I will define this definition in very simple way. So we know from the module number 1 the concept that how to induce the pre-stressing. So through the cable we are going to apply the compressive force on either ends. Okay, we are going to induce a pre-stressing force of certain magnitude through the cable. Okay, it may be parabolic or whatever through the cable. So whatever the pre-stress I am going to induce, that will be called as during the stage of transfer. During the stage of transfer, I hope I have been solved the problems on this particular condition. That is, one is transfer condition, another one is working condition. So I'm going to induce this pre-stressing force through the cable inside the pre-stressed concrete beam during transfer condition. Okay, so after transferring the pre-stressing, so till now I have been discussed in module number 1, transferring of pre-stressing force and negotiating or nullifying the resultant tensile stresses developed due to the external. So in this particular module, what I'm going to teach you is, so whatever the pre-stressing force that will be induced through the cable profile, so that pre-stressing force will undergo gradual reduction. That pre-stressing force will undergo gradual reduction with time. That means as the time elapses, whatever the pre-stressing force induced, that may be okay reduced, that may be lost, that may be lost, okay, due to various causes, due to various causes. So that will be termed as loss of pre-stress. Is it clear? So whatever the initial pre-stress or pre-stressing force induced in concrete will undergo gradual reduction with time. Will undergo gradual reduction with time. Okay. From the stage of transfer. From the stage of transfer due to various causes is termed as loss of pre-stress. So very simple. So whatever the pre-stress that was induced in initial stage, that is during transfer stage, that will undergo reduction as the time elapses. So that, okay, losses is called as loss of pre-stress. Loss of pre-stress. Okay. So moving on to the next. So I've been highlighted here this whatever the initial pre-stress induced, okay, during the stage of transfer will undergo reduction due to various causes. So what are those various causes? So that is what the next topic. The types of loss of pre-stress. Because of these causes, okay, the whatever the pre-stress impose that has been induced, okay, initially or during the stage of transfer, so that will undergo loss. Okay, so let me know the different types of losses encountered in pre-tensioning and post-tensioning system are compiled in table below. So now the very important thing we need to know here, the losses is going to happen. Okay, the losses is going to happen in the pre-stress concrete depending upon the systems of pre-stressing. Depending upon the systems of pre-stressing, the losses is going to happen in the PSC beams. So that systems are, as I stated, pre-tensioning system, you will come across certain losses. In post-tensioning system, you will come across certain losses. Because in both the cases or in both the systems, the types of losses will differ. Why? Because the what I can say that depends upon the material and the material compatibility. Okay, because as I stated in pre-tensioning, okay, the concept of tensioning is different. In post-tensioning, the concept of tensioning is different. So based on this tensioning concept, so these pre-tensioning system losses and post-tensioning system losses will differ. So let me see what are those losses. So coming to the first loss in the pre-tensioning system, the first losses that is going to occur or that will reduce the pre-stressing force or pre-stress, sorry, is elastic deformation of concrete. So as we know, the two parameters or two materials will come into the picture that will undergo the reductions or will make a initial pre-stresses to get reduced because of concrete and steel. Because of this concrete and steel, so this whatever the initial pre-stress I am going to induce through the cable will undergo gradual reduction or will undergo gradual loss as the time elapses. Okay, so because of these two material, okay, the losses is going to occur. So let me know okay, next. So the elastic deformation of concrete is number one. Relaxation of stress in steel, that's what I've been told in pre-tensioning. One is, so as I stated, that will be in the concrete elastic deformation, and one more loss is the relaxation of stress in steel. Okay, next, shrinkage of concrete. So again, the losses that is going to happen due to the shrinkage of concrete. Next, creep of concrete. Okay, so these are the losses that will be encountered in pre-tensioning system, okay, which will finally in turn reduce the pre-stress that has been induced in during the transfer stage. So you can see the concrete and steel will be the root cause for this, what I can say, the loss of pre-stress. Is it clear? So three losses from the concrete and one loss in the steel, okay, that is going to happen in the pre-tension system, in turn will make a pre-stress to undergo the loss of pre-stress. Is it clear? So this is regarding the pre-tensioning. Let us go with the post-tensioning. In post-tensioning system also, this elastic deformation of concrete is going to happen. But here a small change is going to happen. The small change is if all the wires are simultaneously tensioned. If all the wires are simultaneously tensioned, that means whatever the cables have been put. For example, if I am going to put a one cable, I am going to tension one at a time. Am I right? No need to worry. But if two, three or four number of cables has been put inside the concrete beam, and if I want to tension those cables, so then the concept will differ. This elastic deformation loss will differ. How? If all those three or four numbers of wires I'm going to tension, okay, together or simultaneously, then there will be no loss due to elastic deformation in the case of post-tensioning. Please note this point, okay, because all these things are very important in the case of a, okay, while doing the analysis. So that's why, okay, I'm going to mention, if all the wires are simultaneously tensioned, then there will be no loss due to elastic deformation. So the elastic deformation loss will be zero if all the wires are tensioned together in the case of post-tensioning system. Next, if the same wires, if the same, that means a 3 number, 4 number, or any number of wires are successively tensioned, or I can say tensioned one by one, that are tensioned one by one. Okay, so then what I can say, the losses that is going to occur, that means this elastic deformation loss will going to occur, okay, in the pre-stressed concrete beam. So these things is very, very important. You need to note down. If all the wires are tensioned together, no loss due to elastic deformation in post-tensioning. If those wires are tensioned one by one, then there will be loss of pre-stress due to elastic deformation of concrete. Next is relaxation of stress in steel. The same thing. Whatever the losses that was there in the pre-tension, here also the same thing. The relaxation of stress in steel is going to happen. Next, this relaxation, which I'm going to, how it is going to happen, I'm going to explain next. Next, shrinkage of concrete, same thing. Creep of concrete, same thing. Apart from these four losses, as mentioned in pre-tensioning, the two more losses that is going to occur or happen in the case of post-tension beam or post-tensioning systems are friction loss, and another one is anchorage slip. Friction loss and anchorage slip. Friction between the concrete and steel, and the slip of those, what I can say, the wedges that has been put in the steel to tension. So because of these two additional losses, the loss of pre-stress that is going to happen in the pre-stressed concrete beam. So these are the different types of loss of pre-stress you are going to come across in the case of pre-tension pre-stressed concrete beam and next post-tension pre-stressed concrete beam. Okay, so please note down. So based upon the system or based upon the type of a pre-stressed concrete beam, you need to calculate or analyze, or you need to come across the loss of pre-stress in the particular beams. Okay, from the examination point of view, okay, they are going to ask this. So it's a very important. So list the various types of losses. Okay, so at that particular instance, you please, okay, write down in this particular way. That means compile these, okay, in the table and write down specifically so that they can award full marks to you. Is it clear? So now I have been listed now. So let us discuss in detail. Let us discuss in detail how all these losses that is going to happen in the pre-stressed concrete beam. So let me move on. So the first loss, as I stated, okay, so now I'm going to consider the losses together. Now I'm not going to discuss this, okay, because all the four losses, okay, will be same in the pre-tension and post-tension. There is a slight differ in the elastic deformation. But regarding this relaxation, shrinkage, creep, all those things are same. So hence I'm not going to put heading pre-tension losses, post-tension losses again. So I'm going to discuss one by one. So as we know from the table, the first loss is loss of pre-stress due to elastic deformation. So you know what is the meaning of elastic deformation? The elastic deformation means once the concrete or whatever the cable that has been put inside the concrete beam, whatever the cable that has been put inside the concrete beam and tension, and later on I'm going to pour the concrete, and later on I'm going to allow it to cure or get hydrated. So this process you already know from the basics of concept of pre-stressing. So after this, you can see from the diagram the concrete will undergo certain deformation. The concrete will undergo certain deformation as the time elapses. Okay, and this, whatever the deformation that is going to happen, that will be within the elastic range. So whatever the deformation that is going to happen, that will be within the elastic range. That means, let me see what is the reason for this deformation. So once if the concrete beam has been subjected to the this pre-stressing force and the external load. So we know from the module number 1, the PSC beam will be subjected to, one is pre-stressing force, another one is external load. So once the PSC beam is subjected to this pre-stressing force or the external load, the concrete will undergo certain deformation within the elastic range, okay, as the time elapses. So after a certain time, so this concrete will undergo, you can see here, so this the solid line which indicates, okay, that, okay, this was the initial length, I can say. And once the concrete undergoes some elastic deformation, you can see the length has been reduced. Okay, and this deformation within the elastic range. So please note down, this is very important. That's why it is called elastic deformation. The concrete, when it is subjected to external load, that is stressed. When the concrete will undergo stress, it will undergo certain deformation. That is what change in length. That is, you're going to measure the strain. Okay, so whatever the strain that is going to happen due to the effect of stress, so that will be within the elastic range. So that's why it is called elastic deformation of concrete. Is it clear? So this is regarding elastic deformation. And this elastic deformation that is going to happen in the concrete will depend upon the so many factors. What are those factors? So those factors are, one is modular ratio. What is that modular ratio? The modular ratio is defined as we know, in the concrete we have two materials. Am I right? One is concrete, another one is steel. The ratio of steel and concrete, the ratio of, that is the modulus of elasticity of steel to the modulus of elasticity of concrete will be called as modular ratio. If the modulus of elasticity of concrete and steel differs, okay, then automatically the elastic deformation will also change. Next, the one more factor that will depend is average stress in concrete, average stress in concrete at the level of steel. Okay, so what will be the stress in concrete at the level of steel? Okay, so depending upon these two factors, one is modular ratio and another one is the stress, okay, in concrete at the level of steel. So based on these two factors, okay, the loss of pre-stress due to elastic deformation of concrete is going to vary. Is it clear? So fine. So I have been explained the diagram. You can see. So this will be the, okay, this will be the central axis. Okay, and this will be the PSC beam, and this you can see the straight cable has been induced with certain eccentricity. Okay, with certain eccentricity have been induced, and have been induced the pre-stressing force of magnitude P. So now you can see FC is the pre-stress. So this will be the pre-stress developed inside the concrete, that is compressive stress. Okay, FC indicates compressive stress developed in the concrete at the level of steel. Why? Because I need to create a pure compression inside the PSC beam in order to counteract the tensile stresses. And these things you people have already been analyzed in the module number 1. Okay, so FC indicates the pre-stress in concrete at the level of steel. So here it will create a FC. Next, ES is the modulus of elasticity of steel. So we know, okay, from the basics, that is 2.1 into 10 to the power of 5 Newton per millimeter square will be the modulus of elasticity of steel. Next, EC, modulus of elasticity of concrete, that is, which is equal to 5,700 root FCK. So I think I've been discussed in stress strain characteristics. So this modulus of elasticity of concrete can be determined in two ways. So this is the theoretical modulus of elasticity we can find once if you know the compressive strength of a concrete. If you know the compressive strength of the mix or the concrete, we can calculate the modulus of elasticity of concrete. Okay, the another way, okay, the accurate way, or I can say the exact way we can determine is experimental method. So from the experimental method, how we need to apply the load, okay, on the concrete beam, and within the elastic range we need to draw the stress strain curve. So based upon the stress strain curve you need to draw the tangent, okay, and based upon the secant modulus you draw the slope and calculate the stress and strain, substitute in the modulus of elasticity formula, and you are going to calculate the modulus of elasticity. That is EC is equal to stress by strain. Okay, so by this you are going to calculate the modulus of elasticity of concrete. Is it clear? So now, as I stated, the modular ratio is equal to ES by EC, which is very much required in the case of elastic deformation of concrete. So next, if you know what is the stress in concrete at the level of steel, if you want strain in the concrete at the same level of steel, then the stress in concrete at the level of steel divided by modulus of elasticity of concrete. So this will get you the strain in concrete at the level of the steel. Next, the stress in steel corresponding to the strain. Stress in steel corresponding to the strain is given by Fc by Ec into Es. Okay, so the stress in steel corresponding to this strain equal to, so this factor multiplied by the modulus of elasticity of steel. So which will get you stress in steel. So therefore, loss of pre-stress equal to, so what is the value of this? Es by Ec. So this Es by Ec is nothing but alpha E. Substitute that. Okay, alpha E and Fc will be retained same. So therefore, loss of pre-stress is equal to alpha E into Fc, where Fc is the stress in concrete at the level of steel, okay, which is purely compression, is given in Newton per millimeter square. So next, okay, how to quantify this or how to calculate this Fc? We know how to calculate alpha E, how to calculate the Fc. So this is the formula we are going to use to calculate the stress in concrete at the level of steel, that is Fc, which is given by P by A plus PE by I into eccentricity minus M by E into eccentricity. Okay, so there is a small change in the formula. Okay, PE by I into E minus, that means what will be this bending stress at the level of this? What will be the, what I can say, the stresses due to dead load and live load at the level of this? Okay, so based on this formula, I'm going to calculate the stress in concrete at the level of steel. So once if you know Fc value and once if you know alpha E, that is Es by Ec, substitute in the main formula and calculate the loss of pre-stress due to elastic deformation in the concrete. So like this, we need to calculate the, okay, loss of pre-stress due to elastic deformation for pre-tensioned case. Next, let me go with the post-tension, because here the two systems will differ and have been written here. So now, if a number of cables are pulled simultaneously, then there will be no losses, as I stated. So now, the loss of pre-stress will become zero. The loss of pre-stress will become zero when all the cables are pulled together in the case of post-tension PSC beam. If the same number of cables are pulled one by one, then there will be loss of pre-stress. So that loss of pre-stress will be calculated or determined by the same formula, that is loss of pre-stress is equal to alpha E multiplied by Fc. Is it clear? So like this, we need to calculate the loss of pre-stress due to the elastic deformation of a concrete. So next, if the initial stress in the steel is known, the percentage loss of stress in steel due to elastic deformation can be, that means whatever the stress that has been induced inside the steel, if you know that, then you can easily calculate what percentage loss that has been occurred, okay, inside the PSC beam due to this elastic deformation. Because if you know what is the initial pre-stress, so this is the final pre-stress, I can say. Is it clear? So based upon initial and final, we can calculate the percentage of loss of pre-stress in the PSC beam. So this I am going to teach you, okay, while doing the problem. Is it clear? Next, let me move on to the next losses that is going to happen in the concrete. That is loss of pre-stress due to shrinkage of concrete. Okay, so you already know what is the meaning of shrinkage. The shrinkage is defined as change in volume of a concrete due to the change in volume of concrete due to the internal changes. So as I stated, the shrinkage will depend upon this various factors, that is cement, water cement ratio, aggregates, the type of aggregates, all those things. So if these things vary, the shrinkage will vary. If shrinkage varies, automatically the loss of pre-stress is going to happen. So with this context, let us know further. The shrinkage of concrete in PSC member results in shortening of tension wire. That's what I've been told, and hence contribute to the loss of pre-stress. So this shrinkage of concrete in PSC member will result in shortening of tension wire. So whatever the wires have been put in, okay, by tensioning inside the concrete beam, okay, will undergo deformation or will undergo change in length, or it will undergo shortening in length, okay, which will contribute to the loss of pre-stress. So this, as I stated, the shrinkage of concrete will depend upon the so many factors, that is the type of cement, okay, aggregates you are using, method of curing you are using. So based on these, okay, the factors, that is type of cement, aggregate, and method of curing, the shrinkage will vary. Is it clear? Use of high strength concrete with low water cement ratio results in reduction in shrinkage and consequent loss. So as we know, preferably in pre-stressed concrete members, we are going with a special concrete called high strength concrete. So as we know, high strength concrete we are going to attain with a low water cement ratio. Okay, so a reduction in water cement ratio will get you the high strength concrete. So in turn will reduce the shrinkage also, because no water is available inside the concrete, or lesser water is available to undergo shrinkage in concrete or consequent loss of pre-stress. Next, the primary cause of drying shrinkage is the progressive loss of water from, that's what I've been told. If more water present inside the concrete, there will be enormous evaporation of water. This we know from the concrete basics. Because so whatever the water that will be present, okay, that will be mixed in the concrete, so those water is going to evaporate as the time elapses. So as the water evaporates from the concrete, it will undergo certain losses. So those losses is called shrinkage. So as we know, there will be various types of shrinkage, that is drying shrinkage, plastic shrinkage, autogenous shrinkage, carbonation shrinkage, so and so on. Is it clear? So based upon the constraints inside the concrete member, so it will undergo particular types of losses. Next, the rate of shrinkage is higher at the surface of the member, hence proper curing is essential to prevent shrinkage cracks. So the rate of shrinkage is more or higher at the surface. So we need to be very cautious at the particular, I can say, place, mainly at the surface. So this can be avoided by proper curing. So if you do the proper curing, you can prevent the shrinkage cracks in the PSC member. Is it clear? Next, in the case of pre-tensioned member, generally moist curing is resorted into in order to prevent shrinkage until the time of transfer. Okay, so please note down. So in order to prevent the shrinkage, okay, the moist curing is resorted, okay, until the time of transfer. Okay. Consequently, the total residual shrinkage will be larger. That means the left out, okay, shrinkage strain will be larger in the case of pre-tension member after the transfer of pre-stress in comparison with post-tension member. So in comparison with post-tension member, particularly after the transfer of pre-stress, this shrinkage loss will be more in the case of pre-tension, where a portion of shrinkage will be already taken place by the time of transfer of stress. That means some of the shrinkage that is going to happen during the time of transfer of pre-stress, and the remaining part of shrinkage that is going to happen after the transfer of pre-stress. That means during the transfer stage, the shrinkage will be initiated. Is it clear? So now I've been explained the shrinkage. So now how to quantify this? How to quantify the loss of pre-stress, okay, that is going to happen due to the shrinkage. So for that, the Indian code has given certain recommendations, you can see here. So the as per consideration in the recommendation made by the Indian Standard Code, okay, 1343 2012, or the earlier code is 1980. So this is the codal provision we are going to follow for analyzing and designing. You can get some of the formula, this formula in the 1343 codes. One is 1980, the earlier version. The present version is 2012. Okay, for the loss of pre-stress due to shrinkage of concrete. Okay, so the loss of stress is equal to epsilon Cs multiplied by Es. Loss of stress is equal to epsilon Cs multiplied by Es. What is that epsilon Cs? Total residual shrinkage strain having a values, certain values, for pre-tension, which is equal to 300 multiplied by 10 to the power of minus 6. For post-tensioning, which is equal to 200 multiplied by 10 to the power of minus 6, divided by log to the base 10 into T plus 2, where T is the age of concrete at transfer in days. Is it clear? So this is the two, okay, I can say ways I can calculate, okay, the, what I can say, the loss of stress, stress or pre-stress due to shrinkage of concrete. Is it clear? So this epsilon Cs will vary based upon the pre-tension and post-tension. Is it clear? Fine. Next, let me go with the next. Loss of pre-stress due to creep. Again, this loss that is going to happen in the concrete. So it is creep loss. So let me define what is the creep. The sustained pre-stress in concrete of a pre-stressed member. Okay, that means it is a time dependent deformation. That means as the time elapses, the concrete will undergo certain deformation due to the external load variations or changes. So that is called creep. So the difference between shrinkage and creep is both will undergo deformation. The shrinkage, in the case of shrinkage, the deformation will undergo due to the internal variation, but in the case of creep, the deformation that will be very due to the external variations. Is it clear? So therefore, next, the sustained pre-stress in concrete of a pre-stressed member results in creep of concrete, which effectively reduces a creep of concrete, which effectively reduces the stress in high tensile steel. So whatever the stress that was there in the high tensile steel initially, so that will be undergo gradual reduction or change, or will get lesser, okay, because of the creep of concrete effect. Now, once again, the loss of stress in steel due to creep of concrete can be estimated same as that of shrinkage if the magnitude of ultimate creep strain and creep coefficient is known. So now very important, okay, so this loss of stress in steel due to creep of concrete can be estimated by the two methods. One is magnitude of ultimate creep strain method, another one is creep coefficient methods. So based on these two, I am going to estimate the loss of stress in steel due to creep. So first one is ultimate creep strain. Okay, let me go with ultimate creep strain. So let me consider epsilon Cc, which is ultimate creep strain for a sustained unit stress. Ultimate creep strain for a sustained unit stress in a PSC beam. FC we know already, compressive stress in concrete at the level of steel in Newton per millimeter square. ES, modulus of elasticity of steel in Newton per millimeter square. So finally I will get you, Okay, loss of stress in steel due to creep of concrete equal to epsilon cc, that is creep coefficient, multiply by stress in concrete, the level of steel fc, multiply by modulus of elasticity of steel. Okay, so this product will get you the loss of stress in steel due to creep of concrete. Next method is creep coefficient method. Okay, creep coefficient method. So this phi is called creep coefficient, epsilon c is called creep strain, and then epsilon e is called elastic strain, and alpha e we already know, that is modular ratio, which is given by es by ec. fc we know, stress in concrete at the level of steel. ec and es you already know, it is modulus of velocity of concrete and steel. So this creep coefficient is equal to creep strain divided by elastic strain. I will repeat, creep strain divided by elastic strain, okay, will get you the phi value. So that is phi is equal to epsilon c by epsilon e. Okay, the creep coefficient phi is equal to creep strain epsilon c, elastic strain epsilon e. So therefore, if you want to calculate the stress in steel, okay, at the, you can say, you can see here, you can see the stress due to creep of concrete can be calculated by phi into epsilon e. That means I'm going to cross multiply this. So this epsilon e will go here. So therefore epsilon c is equal to phi into epsilon e. So therefore epsilon c is equal to phi into, so what is alpha? Okay, epsilon e, which is given by fc by ec. So that is elastic strain, which is equal to fc divided by ec. Okay, so by this, okay, we are going to calculate the strain in concrete. Next, the loss of stress in steel is equal to epsilon c, that is strain in concrete multiplied by the modulus of elasticity of steel. So this will get you loss of stress in steel. So rearrange that. So we know what is epsilon c, okay, which is fc divided by ec. Substitute that, multiply by ec. Therefore, we know already what is the value of es by ec, which is alpha e, that is modular ratio, that is phi into fc into alpha e. So like this, we are going to calculate the loss of stress in steel due to, okay, the shrinkage, sorry, creep of a concrete. Is it clear? So once again, the magnitude of the creep coefficient varies or depend upon humidity, concrete quality, duration of applied loading, and age of concrete when loaded. So at what particular age the concrete has been loaded, okay, how many duration it has been loaded, what is the intensity it has been loaded, okay, so all those things will affect the creep coefficient factors. Next, the next loss is loss of pre-stress due to relaxation of stress in steel. So this above three losses was there in the concrete. Now the losses that is going to encounter in the steel. So therefore loss of stress due to relaxation of stress in steel. That means the steel will undergo certain relaxation. So once it has been loaded, it will come back to its original position. So that is called relaxation. So which will be given by percentage of relaxation that is going to happen multiply by initial pre-stress in the steel, which will get you the loss of stress due to relaxation in Newton per millimeter square. The Indian Standard Code recommend a value varying from 0 to 90 Newton per millimeter square for stress in wire, varying from 0. FPU to 0. FPU means ultimate stress in steel. Okay, ultimate stress in pre-stressing steel. Is it clear? So this is the formula you are going to use to calculate the stresses in due to relaxation of stress in steel. Next, loss of pre-stress due to friction. So now please observe here, till now we have been discussed the losses for pre-tensioning system. So now as I stated, two more losses that is going to add. So those two more losses are frictional loss and anchorage slip. So that is, in the case of post-tension member, the tendons are housed in the ducts. You know that the tendons are housed in the ducts. These ducts are either straight or follow a curved profile depending upon the design requirement. For example, if you want to put a cable profile of parabolic, then you cannot go with a straight duct. You need to go with a curved duct itself.
So based upon the profile of the cable, you need to change the shape of the duct. Consequently, on tensioning the curved tendons, loss of stress occurs in the post-tension member due to friction between the tendons and the surrounding concrete. So the frictional force or the friction that will be developed between the tendon, okay, which it is going to get bonded to the surrounding concrete. So between these two material, the friction will, okay, vary, or the friction will undergo some losses. So this is what loss of Priestess due to friction. So let me go ahead. The magnitude of this loss is of following type. The loss of stress due to curvature effect. The loss of stress due to curvature effect. That means which depends upon the tendon form or alignment, which generally follows a curved profile along the length of the beam. So once you put or this curvature effect majorly will come across in the case of what I can say a curved profile cables. So in the case of curved profile cables, so this curvature effect will come into the picture. Is it clear? So next, loss of stress due to wobble effect. Okay, because of wobbling of a cable, so this loss will occur. So which depends upon the local deviation. That means deviation of a cable which you have been placed from the alignment. Okay, so from the alignment, if the cable which is going to deviate, so thus deviation will undergo because of the wobbling or wobble effect in the cable. Is it clear? So these are the two losses or effects that is going to come across. Okay, in turn that will undergo loss of stress in the PSC members. So let me go this. You can see here. Okay, so this will be the central axis, and this will be the what I can say the parabolic cable. Okay, so this will be the parabolic cable. Okay, through this, okay, I'm going to induce what I can say the jacking. So this will be the jacking end. You can see. So the cables will be jacked. Okay. So now this is the distance. Okay, where the initial Priestess or magnitude will be induced. You can see here the magnitude of the Priestess-ing force Px at a distance x. Okay, from the tensioning end. So from this end to this end can be exponential function of this type. That is Px is equal to P suffix O multiplied by e to the power of minus into mu alpha plus kx. So this is the formula we are going to come across in order to calculate what I can say the loss of Priestess due to the what I can say the friction. So simplifying this, which will be equal to the loss of Priestess in steel, equal to due to friction equal to P naught into mu alpha plus kx. Okay, so where I'm going to substitute will be considered smaller, so hence it will be mu alpha plus kx. Where P suffix O is the Priestess-ing force at the jacking end. Okay, Px I can say the initial Priestess in the steel. Okay, next alpha is the cumulative angle in radians through which tangent to the cable profile has turned between any 2 points under consideration. So this will be your angle alpha. You can see here. So this will be your angle alpha. This will be the angle alpha. Next, K, frictional coefficient for wave effect. So the K is the frictional coefficient, for the waving effect. So alpha, you know what is the mu, that is coefficient of friction between cable and duct, and X is the distance where the Priestess force is applied. So IS code recommends following values for I can say the mu, that is coefficient of friction between cable and duct. So it depends upon the surface, whether it is smooth concrete or steel fixed to duct or steel fixed to concrete, all those things. So based upon that, we can increase the coefficient of friction. Is it clear? And once again, the coefficient for wave effect, that is K, which is 0.15 meter per 100 meter for normal condition, 1.5 per 100 meter for thin wall ducts and where vibrations are encountered. That means the wave effect will be more in the case of thin wall and the vibrations. For normal condition, the wave effect will be only just 0.15. Is it clear? Fine. So let me go ahead. Okay, the very important thing. So this will come across while analyzing the problem or while calculating the loss of Priestess. Now please note down here, if the cable is pulled, if the cable, the first condition is, if the cable is pulled from one end, if I'm going to pull the cable from one end, that is jacking, then especially for a parabolic cable, the slope is given by, the slope, this is what a slope you can see, which is given by 4 into E by L, where E is the eccentricity and L is the length of the beam. So now for this particular case, if it is pulled from one end, so now for a parabolic cable, alpha, that is slope, is equal to, okay, or alpha is equal to, sorry, alpha is equal to, we know what is alpha. Okay, what is alpha? You already know. I have been explained. Cumulative angle in radians through which tangent to the cable profile has turned. So this is what? So this is what an angle. Okay, you can see I've been drawn the tangent to this cable profile. I've been drawn the tangent to this cable profile. So where exactly it meets the point of intersection. So from that particular end is called alpha. So this alpha, which is equal to twice the slope, that is 2 into 4e by L, okay, for parabolic cable, and x is equal to L for a parabolic cable. So when you come across with a linear cable, instead of parabolic cable, if I put a straight cable with the same one end jacking, so then the same formula, no change, 2 into slope on x is L, but there is a small change in the slope formula. For parabolic cable, it is 4e by L. For linear cable, it is 2e by L. So this is a small change you need to observe, okay, or vary based upon the shape of a cable. Is it clear? Next, we'll discuss the second condition. For a same pre-stressing force for a same cable, if I am going to pull from both ends, in the previous case I was pulled from one end, in this case I have been pulled from both the ends. At that particular instance, you can see, and now please observe here, in the earlier I have used parabolic cable example, and here I can use the linear cable example. In both the cases, okay, so once if I'm going to pull from both ends, the slope formula is 2e by L. For one end, it is 4e by L, and for, okay, this 2e by L. Okay, so now, so please observe this. So please strike off this. Okay, so this is not a formula. So next, so for linear cable, it is alpha equal to slope, which is alpha equal to 2e by L, and x is equal to L by 2. For parabolic cable, alpha is equal to 4e by L. Okay, for linear cable, it is 2e by L. Okay, and for this parabolic cable, it is 4e by L, and x distance is L by 2. Okay, in the previous case, it was twice the slope, and in this case, it is just a slope. So this is the difference between, okay, a cable pulled from one end and both end. That is the one difference. And another difference is based upon the shape. Okay, if it is okay, parabolic, it is twice this. Okay, I can say 4e by L. If it is linear cable, it is 2e by L. So this is the two things it will differ. So this condition you are going to come across while calculating the loss of pre-stress in the pre-stressed concrete beams. So let me, okay, hope you have understood. Let me move further. The next loss is loss of stress in the concrete due to anchorage slip. Anchorage slip, what is that? In most, okay, so this friction loss and anchorage slip loss, as I stated, will come across only in post-tensioning system. So now in the most of post-tensioning system, when the cable is tensioned and the jack is released, please observe, when the cable is tensioned and jack is released to transfer the pre-stress to the concrete, the friction wedges, that means whatever the wedges which have been showcased in the module number 1, why the wedges has been put? In order to induce the tensioning through the cable. So those wedges will get loosened, okay, and automatically whatever the wedges have been put, okay, so that will loosen, so those grips will be loosed. So that whatever, okay, that will be loosened, okay, automatically those wedges will undergo certain slip. So those slip will come across over a small distance. Okay, so that will be called anchorage slip. So whatever the wedges that has been anchored, so that will undergo certain, okay, what I can say, loosen. So that will be called as slip. And this slip will be very minute and very small in magnitude, maybe in millimeter, maybe in millimeter. Okay, so those magnitude of slips will depend upon the two types. That is, one is type of wedges, and another thing, what will be the stress in where I'm going to induce. So based on these two factors, the magnitude of slip will vary. So next, the magnitude of loss of stress due to slip in anchorage can be computed by a formula. Delta is equal to PL. Okay, this is the formula. Okay, so with a slight modification, you can see here the loss of pre-stress due to the anchorage slip will be is equal to. So this formula we are going to use to calculate the loss of pre-stress due to anchorage slip in the concrete. So delta. So you got this formula being de-altered here, where delta is the slip of anchorage in millimeter, L is length of cable in millimeter, A is cross-sectional area of cable in millimeter square, ES is modulus of elasticity of steel in Newton per millimeter square, and pre-stress of concrete, okay, pre-stress in force in the cable in Newton. So as we know, that is a formula, basic formula, that is anchorage slip is equal to PL by AE, where E is the modulus of elasticity of steel. Okay, therefore, loss of stress due to anchorage slip, we know that is P by A, substitute that. Okay, therefore, ES. Okay, ES, so just cross multiply. ES multiply by delta, okay, divided by L, okay, will get you the this loss of pre-stress. So I have taken out this P by A. Okay, so that, okay, so that is what I can say, load by area. So those load by area will be called as what? Stress. Okay, therefore stress is equal to this ES delta by L. So therefore, finally, loss of stress due to anchorage slip is equal to delta ES by L. So this is the formula you are going to use to calculate the loss of stress due to anchorage slip in the pre-stress. So these are all the losses you are going to come across, okay, while, okay, calculating or while analyzing the PSCB. So in the module number 1, you just learned how to transfer the precessing force in the cable. So in this module number 2, what you people are came to know or learning here is whatever the pre-stressing force that has been induced, so that initial pre-stress which come across in the module number 1 will undergo certain losses. So those losses will vary depending upon the types of tensioning system, that is pre-tensioning and post-tensioning system. So that has been discussed in this particular session. So from the examination point of view, okay, in the module number 2, okay, this is very important. In the examination, they may ask, list the various laws of pre-stress encountered in PSC, or they may ask to explain the each loss, or they may ask explain the each loss in the pre-tension and post-tension pre-stressed concrete beam. Okay, so these things are these formula you need to, okay, learn. Okay, and some of the formulas which is there in IS 1343 2012 code book. So this is the codal provision we are going to follow in calculating or designing. So which I'm going to use in module number 3 and 4 in particular. But in module number 2 also will come across certain formulas in 1343 2012. Is it clear? Okay. So with this, I am going to wind up the today's session. Okay, we'll discuss, okay, this loss of pre-stress. Okay, a few more things in the next class. So with this, I'm going to end the session. Thank you.